Okay, great. It's recording. So now if I share my screen, we should hopefully be able to see share.
Okay.
Right, there you go. I asked it a question. Please tell me your name. It came out, hi, my name is ChatGPT. Can you repeat that, please? It came out with that. So this is the voice one. Let's see if you can hear it when I do it. So when I click this button, it should record my voice. So
Okay.
I'm going to say, what should I ask it? How old are you? How old are you?
So can you get it to speak what it says?
Yeah, it did just speak what it said, but if you can't hear it, that means that it's not, the audio is not shared. So we can spend 1 minute trying to do that. If that doesn't work, we switch to just reading it ourselves. So microphone.
So you heard it through your headphones?
Yeah, it came through to my headphones. So audio settings on the meeting. So let's pick microphone.
Now, can it do that?
It may not be able to. If it can't, then we just abandon that.
Right.
Because the alternative is that it speaks on the mic. You probably wouldn't even be able to hear that.
That's right. It would speak through your speaker, and then the speaker would have to come through the microphone, and then there might be some feedback loop.
Yeah, exactly. Yeah, I can't see a setting for taking input from the output. No. I think we'd have to, I can just turn this off and we read it out. That's the alternative. And then do you think that's better to type it, or shall I get it to listen to what I say?
I'd say type.
Yeah.
Whatever's convenient, but I think if you type it, then we can kind of sort of work together to formulate the question.
Yeah, that's a good idea.
You know what I mean? Yeah.
All right, so then let's get rid of this confusing thing. I can just turn it off.
Okay.
Extension. Turn it off. There you go.
Yeah, and maybe we can do some research to figure out how we can.
Yeah, I think we should be able to loop it through, but I bet it seems pretty non-trivial. So let's do a test question now. So what should we ask it?
Well, we do want to start, maybe try to recreate that conversation you had with the ether, starting with, does the ether exist?
Okay.
Like that.
We spell it with an A or an E, which is your preference?
I've been spelling it with the E just for simplicity.
Yeah.
And also because I'm sort of getting involved with NFTs, and then NFTs are traded in Ether, in Ethereum. I'm trying to, have fun with that word.
Okay. So does the ether exist? So the first answer that I got when I did it before was like this, kind of very kind of in the conventional answer is no.
Yeah.
So in the context of physics, the concept of the ether has been used historically to describe a hypothetical substance or medium that was once thought to be necessary for the propagation of electromagnetic waves through space. However, in modern physics, the concept of the ether has been largely abandoned and replaced by the theory of relativity. In the theory of relativity, space and time are treated as a single entity called space-time, and the propagation of electromagnetic waves is described by the interaction of electric and magnetic fields There is no need for a separate medium like the ether to explain this behavior. So in short, the ether does not exist as a physical entity in modern physics.
Right. So, yeah, that's a pretty standard answer.
Yeah.
So, the question I would have is, isn't space-time a medium? Like, what is the difference between space-time and a medium?
Yeah. So yeah, in the context time is actually medium.
Yeah. Good.
Oh, shall I read it out? Yeah. In the context of physics, space-time can be described as a mathematical structure that combines the concepts of space and time. It is not typically considered a medium in the same sense as the ether was once believed to be. Rather, space-time is a fundamental component of the universe that serves as the stage on which physical events occur. One important difference between the ether and space-time is that the ether was believed to have properties such as density, elasticity, and motion, but relative to absolute space. That's an interesting concept.
Yeah, weird.
Whereas space-time is a geometric concept with no physical properties of its own. In other words, space-time is not a substance or medium that occupies space and can be detected directly, rather a mathematical framework used to describe the behavior of particles and fields in the universe. So while there are similarities between the concepts of ether and space-time, they are not equivalent, and space-time is not typically considered a medium in the same sense.
So it's saying that space-time does not have properties, and yet we do have such a thing as permeability and permittivity of free space.
Yeah.
And so those to me, and in order to calculate the velocity of a medium, there's a formula. These, the velocity is the square root of the elastic properties divided by the density properties, I guess, the inertial properties. And so there is, an equation to calculate the speed of light, right, using permeability of free space. So how can it say that space-time has no properties? I'm just asking that question. I don't know how to ask it that question, but it seems to me that the permittivity and permeability of free space are the properties of space-time. So it's saying that says, whereas space-time is a geometric concept with no physical properties of its own, then what about permittivity and permeability of?
Yeah, I think it seems a bit like it's obviously parroting or paraphrasing what it's had as its input, which is mainly conventional standard physics. And that's why we're getting something out that doesn't seem to quite make sense in a way. And this kind of shows why this whole thing doesn't, to a certain extent, make sense, because like you say, just with space-time isn't a medium, and then you're saying, well, clearly it does seem to have the properties of a medium, but then also it's saying here that the ether is considered was once believed to have properties such as density, elasticity. Well, those kind of make sense to me. But then when it said motion relative to absolute space, it's like, then that doesn't kind of.
Right, because in my mind, the ether is space.
Yeah.
Right. In my model, not my model, in my, in my mind, in my concept of the ether, that ether is space. So it is that which gives us the sensation of space.
Yeah.
Right.
Exactly.
And so it doesn't occupy space. So I agree that it doesn't occupy space.
No.
It is space.
Yeah.
If you, yeah, if
Well, it
that
is
makes
kind of
sense.
is everything if you
Kind of
think
like,
ether.
so did you finish watching my ether video from yesterday?
Yeah, I watched that one. That was good.
And so there's that image with the Bose-Einstein condensate with the little dots in it.
Yeah.
Okay. So the little dots in it is what I'm, calling, they call it a vortex anti-vortex pair.
Mm-hmm.
And then they are spaced out in the BEC. They're spaced out, in a grid-like pattern.
Mm-hmm.
And so that's what gives us this, because there are these vortex anti-vortex pairs in the BEC occupying the BEC.
Mm-hmm.
Without those little dots, you would kind of have no concept of space, because you wouldn't have two things with distance between them to measure anything.
Yeah.
Right? That's how I kind of see it. And so in my, the concept that I'm proposing, that, space is filled with electron-positron pairs, which are the vortex anti-vortex pairs. And that is what creates the electric field, and indirectly the magnetic field, are these little vortex pairs, which
Mm-hmm.
would basically, they would be dipoles, basically.
Yeah.
They would be dipoles. And so, I don't know how to ask it this question, but the question that I have is, why aren't we considering the Bose-Einstein condensate as a potential for the vacuum of space? So space-time, as they want to call it. And maybe it is space-time, right? Maybe space and time do need to be combined, but that doesn't mean it doesn't have any properties. It
Yeah.
has to have properties.
Okay.
Right.
I think, what do you say to having a new chat and sort of starting from the base,
Okay.
like super basics of
Okay. So it doesn't remember what it said before.
Yeah. So ether versus space-time is kind of, I think, because it's representing mainly standard physics, like the experiment that I drilled down on previously was the double slit experiment. And
Right.
that kind of got interesting for me because I didn't understand a lot of how quantum physics is meant to be modeling that, and how in the end it seemed very similar to some of the ether things, which was good for me because I'm kind of learning through ChatGPT
Yeah.
how the ether interpretation of the two slit experiment, but also the standard model interpretation.
Yeah. And you did get some interesting answers out of it, I think, when you went that way.
Yeah, because it's kind of like it ends up being like you're getting a view into the world's information through something that can sort of filter it and give you the bits you're interested in. You can sort of tunnel into it. So if we wanted to tunnel in to any information or knowledge or understanding that relates to your theory specifically, I tried this last night with trying out the 2.7 degrees cosmic microwave background, how that correlated with 2.1 degrees. It was saying, or around that amount, for a phase transition of the Bose-Einstein condensate. And
so there's actually two phase transitions, right? The 2.1 gets us the vortex anti-vortex pairs, and then the second transition at 2.7 is where matter is born. So in that sense, I don't have to contradict the Big Bang.
No.
Because I'm saying, because phase transitions, like if you ever study chaos theory at all, or turbulence or anything like that, these phase transitions usually happen suddenly. Like cymetics, right? Where you have, you turn up the sound and you get a phase transition where it transitions to another sort of, image or whatever. So phase transitions can look like bangs, right? They can happen suddenly, instantaneously. You go from one, that's why they're called phase transitions. From one phase of matter to another phase, or one phase of I don't want to call it matter because the ether isn't really matter, even though it's made of electron-positron pairs. It's not made of atoms, right? And when people think of matter, they usually think of, atomic matter and molecular matter and that sort of thing, right? So, so the phase transition, the 2.7 degrees, which I didn't know about until I started studying the Bose-Einstein condensate, that there even were these phase transitions. I just thought it was quite a coincidence that it had a phase transition of 2.7 degrees Kelvin that brings about the existence of unpaired vortices, right? So the unpaired vortices would be electrons, protons, and ponderable matter that we can, experience.
Okay.
And so the vortex anti-vortex pairs are what give us the sensation of charge.
Yeah.
Right. And so here, like, let's say you have an electron, and then you have the vortex anti-vortex pairs, and they surround the electron and give it the sensation that we perceive as charge. So that's how I see it. It seems logical.
Okay, so the vortex anti-vortex pairs, are they positrons and electrons, or are
They
they
are electrons and positrons, electron-positron pairs that so normally you're taught that when electrons and positrons annihilate, right, or come together, they annihilate,
yeah,
they disappear. So what I'm saying is when they come together, they bind together into the medium.
yeah,
Right, they bind in, so you can separate them out of the medium. We know, like, you hear I think ChatGPT was talking about the virtual, electron positron pairs that can, they're virtual particles, they call them, and they can appear anywhere, and they can put them in their equations. They need to do this in their equations for their equations to work. Right? So they know that they exist, but they call them virtual because they don't have a medium. So they're virtual electron-positron pairs that have to be everywhere, so that at any point they can pull that energy out and use it, at a very short, time scale. And so here's something that maybe most people don't know or they don't realize is when let's take a medium that we all know. It's called salt, sodium chloride. Okay, you have a salt crystal. So when if you shine a light of a certain frequency, I think it's 8 electron volts. If you shine a light onto a salt crystal, the sodium and the chloride ions come out of the crystal, okay, and they're free to move in the crystal. So they're released from the crystal. So that's the binding energy. So if you supply the binding energy of the sodium and chloride, the ions will come out. So now you have unpaired, like it's kind of analogous to the electron positron pairs, right? Unpaired charges that are free to move around in the crystal. When you take the light away, they fall back into the crystal and they release the same energy. So binding energy is energy that's released. It's energy that's released. So whatever the binding energy is of a material, when an electron binds to an atom, you know how they say it jumps down a level and it releases a photon. They call them photons. It releases energy, right? So that electron is binding to the atom, or the sodium and the chloride are binding to each other, or the electron-positron pair are binding to each other. And so when in my opinion, when electrons and positrons come together, they don't annihilate. Instead, they fall back into the medium. They get bound back into the medium, and they release all of their ponderable mass. So they release all the energy. So this is a huge binding energy compared. So when sodium and chloride bind into their medium, which is salt, they lose a little bit of mass. The mass gets released as sound waves, actually, in the medium. And so when electron and positrons come together, in my opinion, they are, so using this analogy, knowing that when particles come together and bind together, they lose energy. the electrons and positrons, they bind together, fall into the medium, and they lose you get two gamma rays, one for the electron and one for the positron. So instead of saying they annihilate, I say they fall back into the medium. They become part of the medium again. Then that's where they came from, and that's where they went back to. So that's why I believe they can pull out an electron and positron anytime they want, because they are always there. They're there. So that's a real imponderable medium that can, that makes mathematical sense. Yeah. So when you plug the electron and the positron into the equation they use to calculate the speed of sound in sodium chloride or any other material medium, you get the speed of light. So when you use the binding energy, when you take the energy that they release as the binding energy, and you take the mass of the electron and positron as the inertial property, as the density property, you get the speed of light. So there, and that's what my paper is called, the medium, a medium for the propagation of light revisited. I talk about that in that paper. Okay. I explained this whole sodium chloride analogy, which isn't my analogy. That analogy came from Dr. Simhoney, who I talked about in my previous video. Okay. So he had a model called, he calls it the EPOLA model. Yeah. EPOLA, the EPOLA model. And so that's, I studied that quite a bit and came to understand it and learned a lot from that, because I didn't realize that when particles come together into another medium, that they release energy. That binding energy is actually energy that's released. You think sometimes, I think you think of binding energy, it takes energy to bind things together. No, you lose energy when you bind things together. And that's it. You have to really think about that. That's a different way, that is the way it is. So,
okay. That makes sense.
It's an important piece of information, I think.
Yeah. With these virtual particles, I was fascinated by the idea that ChatGPT was telling me that when you gain energy, you borrow it from the medium, or like from the virtual particle pool or whatever, but you have to pay it back in short return. And I drilled down on that, and I was thinking, how does it know when it's going to be paid back? Is there a banker keeping track of this, or what's going on there? And it turns out the more you drill down and sort of more I hassled it, it was like, well, there's no bank account. It's basically, it's a statistical thing where, and that completely makes sense and correlates with exactly what you're saying. It's like there's a medium there, and it's got a certain amount of binding stuff, or it's got a fabric, and then obviously if there's something going on here that's changing stuff, there's only so much of it can go on, and the more of it that goes on, the more it's going to stress it or do something that means very quickly it's going to have to untangle or go back to, it's going to want to go back to the normal state. And that's what the kind of borrowing is. It's like statistical, it was very fuzzy about it, but when you really drill down, it's like, well,
it's really just like a conservation law.
Yeah, it's just stuff. And
you can't create or destroy ether. It's you borrow it, and you can pull something out and you can put it back in. It's kind of like a bank account, I guess.
Just makes sense
when you use that terminology.
So when you sort of like, when the electron borrows the energy for being taken out, even though there's not enough energy, it's being triggered by the wave from the particle, the double slit experiment. You can think of that as just that part of ether is changing in some way.
Sorry, my other computer's making a weird sound.
Oh yeah.
I don't know why. Yeah, so the other thing that's interesting about these electron-positron pairs is, and that medium is the medium. I don't know if you spent much of my time on my videos about the ferrocell.
Well, I haven't seen that. Yeah.
You have? Yeah, okay.
I haven't seen the ferrocell one yet.
So I spent a lot of time with the ferrocell. The ferrocell, it's a device that, let me grab. All right, so the ferrocell is a device that looks like this.
Oh, yeah.
My camera. Okay, basically it is a piece of glass. So you have a very thin, let me pull this out. Actually, I'm just going to leave it like this. So we've got a bunch of lights around in a circle, and in between is our two pieces of glass with a fluid between. Okay, and the fluid in between is they're basically nano iron filings. They're nanoparticles, ferrofluid, and you mix the ferrofluid with some other fluid so that it spreads nicely between. You want a very thin layer between the two pieces of glass. And then when you plug this into the light source, so you got lights, LED lights around, when you put a magnet near it, you get these really cool patterns. Okay, you get these really cool patterns. And if I can share my screen.
Yeah.
Okay, let me see. What do I want to share? Okay, let's see. Let me go to OpenSea. I'm going to go to my OpenSea and then I'm going to type in. Do you see? Just want to make sure you're seeing.
I can see ferrobright on your OpenSea.
Okay, so let's see if it finds it. It makes these really cool patterns. Come on.
Actually, it's not showing me any pictures yet.
Yeah, no, I don't know why it's not showing it up. It should be. It's not opening OpenSea. I wonder what's going on. Something weird's going on with OpenSea.
Maybe OpenSea's broken.
Maybe that would be terrible. Oh yeah, crypto's going crazy again. So yeah, open. Oh, there we go.
Oh, there you go. Come back
now.
Ferrobright. It's even auto-completed.
Right, that's just a cool name I picked for. So this is kind of, this one here is the standard image that.
Oh, that one's nice. Pink one.
Right, these are all really cool. Yeah. So basically, so this one here is the polar view. This one here is the polar view. So if I put a magnet, so if I take my ferrocell here and put a magnet right here, it's gonna make, and the lights are surrounded, so you can see these little dots around that represents the LED lights. This is a simulation that I got from a YouTuber named AB Science. So AB Science figured out how the ferrocell worked. I spent years trying to figure out how this thing worked because it made these cool patterns and I just wanted to know how it worked. And so he taught me how it worked, and he wrote some Python code for me to make these images. And so this is really bizarre. You know, just these patterns are amazing, right?
Oh, yeah.
And this simulation is extremely accurate. So this one here, I actually printed it onto canvas because it's so pretty. And amazing. So this is 16 magnets. So there's 1, 2, 3, 4, 5, 6, or it's 18 magnets in here. And so where the black dots are, that's approximately where the magnets are. And this is exactly what it looks like under the ferrocell. Like exactly. So with every, you know, so now I can simulate any magnetic configuration and see what it will look like under the ferrocell.
Oh, is that picture generated there from a program, not a picture from the ferrocell?
No, this is the simulator.
Okay.
This is the simulator.
And the actual ferrocell one looked a lot like that.
It would give the same pattern if I put that under the ferrocell. So I know, like, I haven't tested I didn't test the 18 magnet one, but I know for sure this one here I tested. This for sure is you know, this is what it 4 magnets. So this is a quadrupole, I guess. It's a quadrupole diagram, and this is exactly what it looks like under the ferrocell. And so the ferrocell images, they're not as pretty as the simulation. So the simulation are on my OpenSea for, for sale. for NFT. They've been minted as NFTs for fun. But so the point I wanted to make here is I believe that these electron-positron pairs are analogous to the ferrofluid. So basically I'm saying space is a ferrofluid. It is analogous to a ferrofluid, and a ferrofluid is similar to, what we're seeing now. These images, all we're seeing is just one plane, because the ferrofluid is in a thin layer between two pieces of glass. And we're only seeing, the lights are going around from the outside, and we're only seeing, one slice through the magnetic field. But so these dipoles, I believe, when matter is present. So if in the electron-positron medium, if there was no matter, then they would just line up like you saw in the BEC picture. They would line up in a hexagonal tetrahedron kind of. They would spread out similar to the ferrofluid. So in the ferrofluid is it's called a colloidal, I can't even say it, colloidal solution.
Yeah.
Okay. And that what happens is when there's no magnet present, when there's no matter present, when there's no magnet present, the particles, the little nanoparticles, which are polarizable, right? Because it's, iron filings basically at a nanoscale, they spread out. So they, it's like they have a surfactant on them. The particles have a surfactant that causes repulsion. And so they kind of spread out and homogenize. So when there's no magnet, there's no picture. When there's no magnet, it's just it just looks like a piece of, orange glass, basically. But when you put the magnet there, then the light from the sources that are on the outside reflect off the particles. And that's what you're seeing here. So what you're seeing are the reflections. So this is a very simple program. And all it's doing is it's shooting the lights, shooting the rays, and reflecting off the nanoparticles to create these patterns. And so, I believe that that's what space is, that space is filled with these electron-positron pairs, which are like mini dipoles. They're polarizable. So they're very localized. They're a very localized disturbance. They don't really disturb each other. They actually they're behaving as if they have a surfactant that makes them separate. So in the Bose-Einstein condensate, you see that all the dots are evenly spaced around, right? So there's no imperfection. When there's no imperfections in the BEC, then they're going to self-organize into that kind of a pattern.
Yeah.
Right. And so, but when matter appears, it deforms the perfect medium, and then the dipoles surround the object and basically give us the sensation of charge. Okay. So the interesting thing is, I don't know if you remember, a couple of years ago, they made a big announcement when they took a picture of the very first picture of the black hole, right? First picture of a black hole that they actually put, they had all the telescopes on Earth. It's called the Event Horizon Telescope. All the telescopes on Earth were pointing towards this one black hole called M87. And they produced a picture. And the picture looked exactly like a magnet under the ferrocell, but with continuous lighting. So with this one here, there's discrete lighting. Yeah. So you've got lights, basically, so that's why different you colors, see it. Yeah. But when I put continuous lighting around my ferrocell and took a picture of it, basically you got this sort of black thing, and then you have like a more diffuse pattern on the outside. And the picture they showed of the event horizon, now I wish I had something I could show you right now, but I think I have something in my community section on that, looked exactly like a ferrocell image. And so that's what gave me the idea that maybe this medium, this, polarizable electron-positron pair dipole medium was in fact a ferrofluid, or analogous to a ferrofluid, right? And so otherwise, you know, if that black hole image had looked like anything else, I might not have thought that, but it looked exactly like the image I took of, you know, a continuous light source. So you can imagine a black hole has light coming from all directions, right? And so, and then it's going to reflect off the particles into your eye in a certain way. And it seems to be doing it exactly the same way that the ferrofluid is presenting light to us. So I thought that was pretty, you know, more sort of not vindication, but just more clues as to whether this kind of a medium can exist, and if it does exist, does it explain things better than the standard model?
Yeah.
Right.
You mentioned that there where you said about positron electron pairs being the space medium. That's at the 2.1 degrees equivalent of for the Beck vortex anti-vortex pairs. And then the idea is that later on matter forms more at 2.7, which is the second phase transition. Remind me of what the phase transition is in the Beck. It's you've got the vortex anti-vortex pairs.
So here's what happens, as I understand it, in the BEC. So they're, because we're already in a warm universe, they have to take things and cool it down. So what I'm imagining is that the universe started at absolute zero and either spun up or warmed up for some reason. Okay. And when, you know, a lot of people say, well, where did all the energy come from to, you know, cause this to turn or whatever? And I'm like, well, where did all the energy come from for the Big Bang?
Yeah, exactly.
Where did all the energy come from? I'm going to borrow a little bit of that to start up my BEC, whatever. So the first phase transition this is in a real BEC. In their experiments, they cool everything down to absolute zero, and then they slowly bring it back up. And at 2.1 degrees, you start seeing these vortex anti-vortex pairs. And the higher the temperature, so between 2.1 and 2.7, you get 1, 2, 3, 4, 10, you know, vortex pairs forming. And then at the 2.7 degrees, they start seeing unpaired vortices. So the unpaired vortices appear in, you know, just in between the vortex pairs. And I don't know what that looks like because I don't have a picture of that right now, but this is just what most of the papers I've read on BEC, it's all math. It's hard, you know, there aren't a lot of pictures. It's a lot of graphs and a lot of math, which I'm not going to pretend that I understand all that, but I do understand this. I understand what a phase transition is. And so the second phase transition at 2.7 degrees, above that temperature, that's where matter would have exploded into being. It would have come into being, and it might have looked exactly like the Big Bang, which it might be why we have the Big Bang, right? And so I don't want to contradict the standard model if I don't have to, right? And so this was one way that I could sort of say, okay, so they're saying the universe started as a hot, dense soup, because they're only seeing that moment where, boom, all of a sudden there's matter coming into being. They're not seeing what happened before that. And maybe they see a little bit, because they do have something in their model called inflation.
I've seen TV programs about that.
And then it exploded. So this inflation would be the vortex anti-vortex pairs forming. Because if you saw in my video, I showed there was 1, and then there's like 6, and then like, so each time when there was more, the BEC actually expanded. It expands. So that could be the inflation part that we see in the Big Bang, that is part of their model. It's sort of inflation, and then boom, explosion. So that could have been the 2 phase transitions, in my opinion. The temperatures are very coincidental. Like, I don't believe in coincidences. So the fact that, you know, that they have this 2.7 degrees makes me very suspicious. That's a very important piece of the puzzle in the BEC.
That rung a lot of bells for me.
Yeah, and there's something interesting, like I like analogies, because we're talking about fluids and superfluids and that sort of thing. With water is very interesting. Like has so many interesting properties, right? It's a very bizarre material. So if you have a lake, and the temperature is cooling down, right? The lake has to be 4 degrees Celsius. The whole lake has to be 4 degrees Celsius before any ice can form on top. Any ice
minus, it's 4 degrees, and then
4 degrees. Yeah. So water is most dense at 4 degrees.
Yeah.
Water is most dense, not at 0, not at freezing point, but at 4 degrees. Okay. And the whole body of water has to be 4 degrees before any ice can form. And so that's kind of my analogy. I'm going the other way. I'm going from cold to hot, that the whole universe has to be 2.7 degrees before any matter can form, right?
Can you see how when this 2.7 degrees got hit, could there be anything that you can imagine that would be a feedback process? So as soon as you get you got your vortex, anti-vortexes. Those are the little dots that you saw, where they're all nicely evenly spread. Everything's very nice and calm, and it's gradually becoming more and more something. But then you're saying at 2.7, which could be 2.7 degrees Kelvin's worth of spin, or it could be 2.7 degrees. You said that was fascinating for me, that you can have a Beck at a much lower temperature than 2.7 if you measure temperature just by the conventional method. But if you spin it enough, it does exactly the same as it's almost like spinning and temperature are almost equivalent.
Are related. Yeah.
It could
They're
be
the same thing almost. Yeah.
Yeah.
So I thought that was fascinating too. Yeah, for sure. Like increasing the temperature and trying to spin a BEC have the same effect. You get these vortex anti-vortex pairs.
That's reminds me a bit of like just our conventional view of temperature. What is heat? What is temperature? It's like, is it movement like this, or could it be more of a macro scale movement? So anyway, so coming back to that, it's when you hit 2.7, you've got your vortex anti-vortex pairs, everything's nice and even. Can you imagine how, when these vortex anti-vortex pairs, they're currently sort of stable, and that means when they're stable, they're forming, each one of those is one of those dots, and that's one of those dots is made of a vortex anti-vortex. Is that what you're saying?
That's how I understand it. Yeah. So I don't really know how that physically manifests, and I don't know how they know that it's a vortex anti-vortex pair. It's hard to kind of, but that's what they're saying. That's what they call them. Yeah.
And then at 2.7, some of them start, not all of them at the same time, but some of them start unpairing. So you're getting.
I think
it forms separately.
They form separately. So it's not like you take some vortex anti-vortex pairs away. It's my understanding that all of a sudden unpaired vortices start to form.
Does that mean you get like a positron here and then maybe an electron somewhere else,
or it might even be it might be electron and proton, right? They wouldn't necessarily have to come in pairs. They're unpaired. So not only are they different in charge, but they're also different in mass. So I don't think positrons form in that. That's just my opinion. It kind of doesn't make sense that electrons and positrons would form, because you're creating an imbalance. This is creating an imbalance. And so I think this is where electrons and then protons are formed. And then, of course, everything else is the same as if it was a Big Bang, basically.
So they see at 2.7 individual vortexes and individual anti-vortexes, whatever. that
Yeah,
is. And for
yeah.
them, they don't call them an electron and a positron
No, they just
or a
call them
proton.
vortex, anti-vortex pairs.
Vortex. So they see a vortex, and
And I
then over
don't
here they see.
know if they see the same circulation in, see, there's a lot that I don't know. There's a lot that I don't know. So after that phase transition, I know they see, some vortices spinning this way and some vortices spinning this way. And I don't know if the ones that spin this way are spinning slower than the ones spinning up, so one, if one was slower than the other one, then that would be analogous to the electron and the proton.
Okay, so in your
In
model,
my
an electron is spinning at a certain speed, and a proton is the same kind of structure but spinning at is it faster or slower?
Yeah. And that's where what I'm calling my own particle model comes in, where the electron is spinning at the Compton frequency of the electron, which is in the order of 10 to the 20 hertz.
Yeah.
And the proton is spinning in the order of 10 to the 23rd hertz.
So it's about 1,000 times faster.
Yeah, so that's where the 1836 mass difference, because the proton is 1836 times more massive than the electron. So it's spinning that 1836 times faster than the electron, which is why it's more massive than the electron. So this vortex spin, in my model, is what gives mass to the particle. And of course, when you're spinning faster, the particle has to shrink.
Yeah.
It's like the skater that, has to move the arms in.
Yeah,
so
exactly.
For conservation of angular momentum, basically. That's why, so it's a nice, it's a nice model. It makes sense, right?
So all of these different types, like the standard model, all the different types of particle, in your model, could you correlate, or do you correlate all of those with just a spinning speed, or does it a spinning speed and direction? I mean, direction is anti and
so spinning one way would be positive charge and spinning the other way would be negative charge, and that is just a schematic.
Okay.
So when I use the yin yang, it's just a schematic. It could be like a source and a sink, right? So it could be sort of spinning in is
down
positive charge and maybe spinning out. So a sink would be spinning in and a source would be spinning out, and they would look like they're going in different directions, even though they're going in the same direction. So it gets a little confusing. Like when you talk about spin and clockwise and counterclockwise, it really messes with your mind, because I can have like a gyroscope and I'm looking at it this way and it's spinning clockwise, and I look at it this way and it's spinning counterclockwise. So you can't say, oh, it's spinning clockwise or counterclockwise, because
there's no absolute frame of reference.
Yeah. But when you're talking about sources and sinks, it makes more sense, because a source would be coming towards you, expanding, and a sink would be contracting, and that is more tangible, I think.
Yeah, it doesn't matter which direction you look from 3D spaces.
So I kind of want to say that protons are sinks and electrons are sources, because you can imagine that sinks can, like, if you had two sinks in your bathtub and they could move and you drained the water, I think those two sinks would try to come together, and protons come together in the nucleus of the atom, right? So protons come together and the electrons don't. Electrons expand around, so they seem more like sources, and protons kind of collect together. They seem more like sinks to me. If I was going to call one a source and one a sink, I would call the proton a sink and the electron a source.
Okay. That sounds good.
Yeah.
I like the idea of everything pretty much looking the same. Like all these different things, but they're basically just
instead of the proton has quirks and the electron has, I don't even know, like, it's the language is kind of crazy. Their language is kind of crazy, which is why, I mean, I'm a computer scientist. I like to think I'm very logical, and I don't like like, you know, the thing that even what ChatGPT was saying about space-time not having any properties. I'm like,
Yeah,
what? How can, I mean,
it doesn't
how
make
can
sense, does it?
space-time not have any properties?
Yeah,
Yeah, but it does, because we talk about the permittivity and permeability of space. And so, but I guess, oh, space has properties, but not space-time. Like, it's the language is messed up, and I don't like that. That's why I always say in my videos, if you watch a lot of my videos, you'll see me saying the problem is with the language. The
mm.
problem, I don't want to like contradict the mainstream physics. I just don't like the language. I think I can re-say it in a better way. I think it could be said differently and still get the same, you know, the same results.
Yeah, if you can
So,
simplify the explanation massively and
yeah,
still end up saying, giving, you know, like you say, getting the same math results,
yeah,
the same physics
yeah,
in terms of what you're predicting, then why it seems like a good idea to look at the much simpler
yeah.
explanation.
And why not? Like, why is it discouraged so much? That's what really bothers me. Why does coming up with a different language, why is that discouraged?
Hmm.
Because, you know, like, there's how many, like 7, almost 8 billion people on Earth. Like, we don't all have to speak the same language.
Hmm.
Yeah, and I know it's useful. Like, they have to have, I understand why they do it. They have to have a standard in order to make progress, so that everyone's speaking the same language, but everyone's speaking like a very bizarre language that no matter how hard I try, it doesn't make sense.
No,
I can't
isn't it not
understand.
meant to make sense? Like according to
I
a lot of
like, are they
people.
doing that on purpose, or is
No,
is
it's just
is
they
everyone
kind
just
of.
happy to plug along with a crazy language, or they pretend to understand it because they want to fit in with the club, and
Mm,
like, I don't know, it doesn't,
yeah,
they seem, it just seems like a crazy language to me, that, and it's inaccessible to the average person, and that really bothers me. I'm trying to, I would like to create something that is accessible
yeah.
to the average person.
We've got in the UK the BBC making quite good documentaries about quantum physics and stuff, and I've enjoyed quite a lot of them. And there's one person called Jim Al-Khalili, who's, I think he's a member of the Royal Society, and he's done lots of popular science things. And I watched quite a few of them on the BBC, and I read as part of this thing in the last 6 months where I've been delving into this. I read one of his books about quantum physics, and I ended up not finishing it because it frustrated me a bit. But I did get as far as reading the beginning of one chapter where he described how he'd ended up describing to his wife how quantum physics works. She generally wasn't interested, but they ended up with a bunch of time when they were having dinner one evening, and she seemed a little bit interested. And so he took his chance and sort of went for it and explained quantum physics to her. And he got to the end of it, and she sort of, I can't remember exactly, but she basically said, "You know what? That's really, really interesting, but," she said, "I don't believe a word of it." He wrote this in the book, and I was like,
Yeah,
actually, that's funny that why is he even writing this? He's writing
yeah,
it because, and then he sort of said he understood her point of view. It's like
yeah,
none of it really makes proper sense,
yeah,
but he wasn't slagging it off. He was just saying, well, this is what we have to deal with. This is how things work
yeah,
according, and he didn't say according to our model. He says, this is what, our science explains it as. This is what we see. I can't explain it any other way.
yeah,
Sorry, this is reality. It is very
yeah,
weird. And that was kind of his way of explaining to the
yeah,
reader why his wife had that reaction. And he understands that it looks very weird, but he's saying that's how it is.
yeah.
But actually,
That's
I think
not
me and
how it
you don't
is.
really come at it like that. We go,
That
okay, well,
that
that's
is
how it
just
is.
how.
If you've learned the standard way of science and you've gone down that whole path and you've absorbed all it and you've gone, okay, you're trapped then in
Yeah,
exactly that. It has to be weird and just
yeah,
shut up and calculate all that
yeah,
stuff.
yeah.
But if you,
It's a huge learning curve, and if you take the time to go down that rabbit hole, you have no choice. If
No.
you want to communicate with your colleagues, you have to use that language. Right. So I don't believe a word of it either.
No.
But I don't not believe it. Like, I just believe that the language is poor. And that it could be explained. Like, I always do this thought experiment. If if the aliens came from another planet, are they going to have the same language? How will we communicate with them to find out what their language is, right? We're definitely not going to be showing them blackboards full of equations,
no.
right? And that they're going to automatically understand our mathematical crazy scribbles, right? They're going to have different crazy scribbles maybe, but like, how would we communicate with them?
Yeah.
Right.
You need simplicity.
The first thing I would show an alien is the picture of the Mandelbrot set, because because they would have seen that, I think. Right.
Fractal nature.
And yeah. I mean, just as, so the thought experiment is, the aliens come down to Earth and they have a contest, and you're only allowed one piece of paper to, to show them something, to show that you're worthy to learn their cosmology. And of course, I would hold up the picture of a Ferrocell, and I would hold up a picture of the Mandelbrot set.
Yeah.
Because those are real tangible things that I'm sure if an alien, because they would know about complex numbers, right? I'm sure, because complex numbers are just two-dimensional numbers. That's the other thing that, I think my language is going to be better right off the top, because I'm modeling complex numbers correctly as two-dimensional numbers. And so the 2x2 matrix formalism of complex numbers is the correct way of looking at it. And so you don't need imaginary numbers anymore. You don't need the square root of -1. Like, you don't need the confusion of the square root of -1. The imaginary numbers are the backward diagonal of a 2x2 matrix, and the real numbers are the forward diagonal of a 2x2 matrix. And I can write a computer program for that without invoking imaginary numbers. I don't have to, or complex numbers even. It's just a 2x2 matrix, transformation matrix. That's all they are. And so the confusion, I think, I don't know, like, why do they have this confusing language for complex numbers when they don't really need to? They don't,
Could have had a much better name.
What's that?
They could have come up with a better name than imaginary number. Come up with like backwards anger
real
model.
numbers are like, the real numbers are on the horizontal axis, so imaginary numbers are on the vertical axis, because I don't know, it's just weird the way they say things. It's just weird. Imaginary numbers, complex numbers are actually very simple, and I call them simplex numbers. In the 2x2 matrix form, they're very simple. It's a little more complicated. Like, when you can add 2x2 matrices together, you can multiply them together, right? And they just become transformation matrices, right? And so almost all of physics depends on complex numbers, but it may be, and probably, the confusing language comes from the fact that they don't understand imaginary numbers. And so in quantum mechanics, they're constantly trying to get rid of the imaginary component. The imaginary component is the backward diagonal of a 2x2 matrix, which is the rotation part of the matrix. It's what causes rotation. And that's why, that's why complex numbers are used to model particles, because particles are spinning, and complex numbers, especially the imaginary component, generates spin. And so I can use my complex numbers, well, any complex numbers, but I can use the 2x2 matrix to simulate my particle spinning, for example, so easily with a few lines of code, right? So I think a lot of the confusion in language comes from the confusion about complex numbers. And so if I did anything, if I could pick one thing that is the most important thing that I'm doing right now, and that's promoting the 2x2 matrix version of complex numbers. and taking the mystery out of the complex numbers and saying, you know, like in quantum mechanics, maybe they don't need to destroy the imaginary component. They always take the imaginary component out. They either square it or they take the complex conjugate, they multiply by the complex conjugate, which also gets rid of the imaginary component. They're always trying, and that's why they can only do things probabilistically. I think if they use complex numbers correctly, they don't have to get rid of the imaginary. The imaginary component is the spin component. And they say, oh, electrons have spin, but it's not spinning. It's just intrinsic spin. Like, what does that even mean?
No, doesn't mean much.
Oh, it's spin. They call it spin. They know it's spin. But because they get rid of the imaginary component, I think they can't really see it as actual spin.
Yeah.
It's imaginary spin. But imaginary numbers are how you model spin in computer science. So as a computer scientist, I know that the backward diagonal of a 2x2 matrix generates spin.
Yeah.
Right. So, you know, I think a lot of the confusion of the language will go away if they start using, you know, complex numbers correctly and teaching it correctly.
Yeah. So with your RM particle model, when I put it into ChatGPT yesterday, it wrote me a little essay, and it seemed to focus in on the 2.1 degrees as the phase transition when I said obviously 2.7.
Yeah.
So I don't think it knew. It probably does know, but it needs to dig more into its brain to find the 2.7 transition to where they become the unpaired vortices. So we could have a try at asking it about that.
Okay.
I'll share my screen. Okay, so yeah, let's ask about unpaired vortices appearing.
So say at what temperature? Yeah.
You see unpaired vortices appearing in a spell out wrong.
No. Oh, yeah.
State.
All right.
Oh, I should read it out. The temperature at which unpaired vortices start to appear in a Bose-Einstein condensate Beck depends on several factors, such as the density of the condensate, the strength of the atomic interactions, and the shape of the confining potential. In a uniform and isotropic Beck with repulsive interatomic interactions, the critical temperature for the onset of vortex formation is given by that guy and that guy and that guy transition temperature, which is approximately equal to blah blah blah.
Yeah. So it's not going to give you a number.
Okay.
So we'd have to do some calculations.
That in Kelvin. H is the reduced term Planck constant, N is the number of density of atoms. Okay. The expression assumes the vortices are created in pairs, which then separate as the temperature is further reduced. This expression assumes the vortices are created in pairs, which then separate as the temperature is further reduced. That's the opposite of kind of
they're going from hot to cold.
Hot to cold. So as they go from hot to cold, they think
they're going from
the vortices are created in pairs at a higher temperature, and then as they go lower, they separate. That's the opposite of. Do you understand this sentence?
Okay, I don't know.
In a uniform and isotropic repulsive, critical temperature for the onset of vortex formation is, I think he's talking about, it is talking about the formation of vortices
Yeah.
Which is probably your 2.1 degrees, is it?
No, that's probably, see, it's confusing because then you say as you further reduce the temperature. So I'm trying to go from 0 up
Up,
if
yeah.
you're going up in temperature. So, they have the normal atoms and then they cool them down and they get vortices, and then the vortices disappear and then you get the vortex pairs. So if they're going from a hot temperature to a cold temperature.
Okay, so let's do it the other way. Can you please explain what a Beck that you are, as you're a spinning Beck?
Yeah.
Spinning Beck. You increase
From 0 Kelvin.
0 Kelvin. In terms of visible vortices, etc. Sure, I can explain what happens in a spinning Bose-Einstein condensate Beck as the temperatures increase slowly from 0 Kelvin upwards. The behavior of the Beck depends on the strength of the external potential, number of atoms, and the temperature. At 0 Kelvin, the Beck is in its ground state, which is a state of minimum energy where all the atoms occupy the same quantum state. If the Beck is spinning, it can form a vortex lattice where the atoms rotate around the axis of rotation, forming a regular pattern of vortices. The number of vortices depends on the angular momentum of the system and the strength of the external potential. Do you know what they mean by strength of external potential? Is that like a magnetic?
Yeah, usually when they're making one of these Bose-Einstein condensates, they've got a material trapped in a magnetic potential of some sort.
Okay.
So, there are a lot of,
To stop it escaping or disappearing.
Yeah, they sort of trap it so that it can't escape, right? So they're trapping it in a potential. Again, these are the details that I don't,
That's fine.
I've done these experiments myself, so I don't really know
That's okay.
how they actually do them, but they do have some. And usually these, their experiments are 2-dimensional.
Okay, they try
So
and
it's like a
flatten
flat,
them out.
kind of like the ferrofluid, the
Yeah,
ferrofluid.
simplify it probably.
Just it's simpler for them to do. Or sometimes I think I found somewhere they're doing like a surface instead of it being flat, it's on like a 2-dimensional surface sphere. But and I think they can do them volumetrically as well. It's just harder to see. Like for 2-dimensional thing, it's easy to see the vortices forming and that sort of.
So as the temperature is increased from 0 Kelvin, the Beck starts to undergo thermal fluctuations, which can disrupt. Okay, this is interesting because
so they're not calling it vortex anti-vortex pairs. They're just calling it vortex lattice.
So that's something that they're saying when you're spinning it is already there from close to 0. You've got your vortex lattice. So that's not the 2.1 degree what he's talking.
It's not saying it the way, like I've read lots of papers and they always talk about transition temperatures. So we should maybe ask it about transition.
Yeah, we'll read this and then we'll sort of pin it down, try and pin it down. As long as we don't ask for a reference, which it will make up. As the temperature is increased from 0 Kelvin, the Beck starts to undergo thermal fluctuations, which can disrupt the vortex lattice and lead to formation of unpaired vortices. So this is this is what you're talking about happening at 2.7.
Yeah.
Unpaired disrupt the lattice. So, okay. These vortices are created in pairs, but can separate as the temperature is further increased. So that's kind of what I was asking earlier. It's a bit so they are always in pairs.
Yes.
But the temperature, once the temperature is higher, they come apart. It's not like you just suddenly get a anti-vortex pair here. Oh no, you don't suddenly get an anti-vortex here and a vortex here. It's always
Are
anti-vortex,
these,
anti-vortex.
they're created in pairs, but are they the same size?
They could all be different. Like it could be tiny, tiny vortex,
Yeah,
anti-vortex, and then a massive, massive vortex, anti-vortex. But they're always paired.
yeah,
And then as the temperature goes higher, they separate.
yeah.
The critical temperature for the onset of vortex formation,
Is given by that crazy formula that they
as
showed
I
you.
mentioned in my previous
Yeah,
answer, that's the vortex pair formation. When there's always pairs, isn't it?
yeah,
Okay, so that's if the temperature is, oh, he's repeating himself now, itself. If the temperature is increased further, the vortices can become more disordered and can move around more freely, leading to more turbulent behavior. At
yeah,
high temperatures, the beck can eventually evaporate where the atoms are ejected from the trap due to their thermal energy. Interesting. Do you know, I'm fascinated by this idea that like you create a beck and it's at 0 degrees and it becomes, it's saying up here, it's like becomes a single quantum entity or something. Is
yeah,
that true?
yeah.
So
So
when
basically they take a material, some atoms of some sort,
like helium is one of the ones they do.
rubidium or
Okay.
rubidium's the one that they use, and they cool it down.
Yeah.
So it's normal atoms, normal matter, because
Mhm.
and then they cool it down. And
Yeah.
when it gets to 0 Kelvin, it's at this one thing, which I refer to in my video as one thing, which is one, it's behaving as if it's one atom
Mhm.
and or one wave function described by one
That's
wave,
that's what it
not.
said earlier. Yeah,
Yeah,
it becomes
yeah,
a one quantum wave function.
yeah,
So then, as it heats up and it does goes through all this process, and then eventually, I'm putting quotes around it, but atoms
yeah,
fly out of it.
yeah, yeah,
We, if we're imagining it from your model's point of view,
yeah,
the atoms that are flying out of it are obviously just kind of formations of
yeah,
vortices and bits
yeah,
all stuck together.
yeah,
But fundamentally, we got it down to this, got it getting it down to 0 just means getting it back to almost pretty much ether
yeah.
in its simplest
It's
or
the
sort of
original
fundamental form.
one thing. Yeah,
Yeah.
that's one. Yeah. Mhm.
Okay. And then
So
are
at the
they
top,
create, would you say that the atoms that come out,
yeah,
are they're not the same? It's not like, yeah, that's the question I've got is like, if you've got, say, a trillion atoms of helium and you put it through this
yeah,
experiment and
yeah,
then you get it down to almost 0 because you can never
yeah,
get to 0, and then it looks like one thing and then you
yeah,
bring it back up.
yeah,
Maybe a standard physicist, would they say one of those atoms of helium got sort of almost looks like it had disappeared, but it is there. And then when you do you reverse it back out, that one atom reappears because it kind of gets untangled from this quantum state. Whereas you and I would probably be more willing to think, actually, you put it down, and then as you come back out, atoms are formed from all the vortices, and
yeah.
it's not the same atom that went in.
It just
Just
looks like
it's just
it would be very similar
ether.
to,
Yeah,
yeah,
ether in the form. Which would you
yeah,
say it is? Does the helium stay? The atom stay and then
yeah.
come
So that
visible?
is a good question. So if they cool down rubidium, then when you bring it back up, rubidium comes out. There's not going to be something
It
else.
wouldn't reform as something else. It always comes back out as rubidium. Yeah.
Yeah, I believe so. Yeah. So that's interesting. That's interesting. How does it know to become rubidium and not? Like if you cool it down to one thing, I
Yeah.
guess that the wave function for the rubidium would be in that,
It'd
the
be
base.
encoded in that wave
It
function, maybe.
coded in that way. Yeah. Yeah.
Or maybe there's some ghostly remembrance of each of the atoms, and then when you
Yeah.
heat it up, those remembrances sort of
Yeah.
reform.
Yeah. Something like that, like a DNA kind of
Yeah.
technology.
So that's interesting.
Yeah, and this is not, I mean, I'm not going to claim to be an expert on Bose-Einstein condenses. It's the math behind it is freakishly complex and
Yeah, I can imagine.
it's scary stuff, really. When you do get into this, the realm of the super cold, things become very bizarre, like superfluids and stuff.
Yeah.
But to me, just just thinking logically as a computer scientist, doesn't it make more sense that the universe started from the absolute zero super cold?
Oh yeah, definitely. Yeah.
Rather than starting from the hot dense soup, where that energy, we have no idea where that energy came from to create that bang.
Yeah.
Right? So to me, it kind of makes more sense that the universe was started at the super cold, and then there's evidence, for this kind of phenomenon in the domain of the super cold.
Yeah.
Right. So there's evidence for formation of vortices, which I am modeling particles as vortices. So, so it makes sense that this is where, it's not the universe was hot and it's cooling down. The universe is cool and it's warming up. And that's a diametric opposite perspective in terms of entropy, right? Because in the hot dense soup analogy, the universe is
we're now cooling and cooling, yeah,
and we're dissipating now, and eventually the universe is just gonna
heat death.
Be nothing. It's gonna be nothing.
Yeah.
They predict that the universe is gonna die into nothingness, and that is not what I observe when I look back at the universe. When I look out into the universe, I see emergence. I see things emerging, and things are continuously emerging. And so in this cosmology, starting with the super cold and warming up, and in the fractal paradigm, when I think of sort of time as sort of an iterative process where things keep emerging and keep emerging, in the fractal paradigm, things don't stop emerging. Right? The universe is not like entropy. I define entropy a little differently. I define entropy as change that cannot be undone. Right. So I define all the terms of physics in using the word change. So time is an emergent property of change. Inertia is resistance to change. So the BEC is resisting the spin. It's resisting being heated up. It's completely resisting any changes. So I define inertia in terms of change, resistance to change. And I define entropy as change that cannot be undone. So it's not the entropy that we're taught, that you were taught, or maybe, maybe you didn't study it, but is the entropy that you're taught of the dissipative entropy is in a closed box. It's in a closed box. So it is an experiment in a box, in a closed system. So entropy is defined for a closed system. Our universe is not a closed system, in my opinion. It's also not an open system. It is somewhere in between. It is an open closed system, just like a circuit. Think of a circuit. A circuit is both open and closed. You have to have a ground. You have to have a ground. You have a circuit, which is closed, but you have to have a ground, which is, open. Like it's, so electrons can come from somewhere. So our universe is not a closed system. It's not a completely open system. It's an open closed system with feedback loops, right? So the iteration process, the output of the equation is going back into the equation. The universe is iterating itself through feedback loops, and that is why evolution happens. So the universe is not dissipating. If the universe were dissipating, it wouldn't have evolution. We wouldn't even have had the amoeba. We've gone from the amoeba to the human being in evolution on our planet that we know of. And so entropy just means change that cannot be undone. Aging can't be undone. Evolution can't be undone, right? You know what I'm saying? Like when you're born, we go through continuous changes that cannot be undone. We're born, we grow up, we grow old. All of those processes cannot be undone. And so that's how I define entropy. So entropy is one of those concepts I think that needs to be maybe defined a little differently to make more sense. So because the universe that I am imagining is not going to dissipate into nothing in the future. It's going to continue to evolve and continue to get more and more complex, right? So, and that's what I learned from the Mandelbrot set. Actually, that's what it taught me, is that complexity increases with time and time, with iteration. So every time I iterate the Mandelbrot set, I develop more and more complexity. It can develop more and more complexity. It actually has an evolution kind of built into it. And so, and you can even see all the forms of evolution in the Mandelbrot set. If you look at it closely, you can see, I can see how evolution can happen in terms of, this iteration process, the feedback loop. The universe, obviously, there's a feedback loop. It's feeding into itself. There's no, like, the energy isn't just dissipating into nothing. It's feeding into itself. And that's why we have complexity, fractal patterns. That's why the galaxies look like kind of fractal patterns, and nature and life and trees, and all of these things would not be happening with the standard definition of entropy.
Yeah, I can see your point. It's like going the opposite direction to how it's been described, which is that everything chaos grows rather than complexity.
ChatGPT here was talking about how, above a certain temperature, you get this turbulence. Well, that's what turbulence is. Turbulence is chaos.
Yeah.
Okay. So it makes more sense that the universe started super cold at the super simple, then the first phase transition, where it's, the first phase transition is sort of where the vortex anti-vortex pairs. It's not a sudden, it's sort of, you get 1, then you get 2, then you get 3, then you get 4. And then you get above a certain temperature, you get the unpaired vortices. And again, you get 1, 2, and then 4, and then 8, whatever. So it's not like, but I don't know, the second phase transition might be more sudden than the first phase transition. I don't know. Because again, I don't know enough about these experiments to know how quickly these unpaired vortices form. Do they form really, really quickly? And does that heat up the back more? Like, is there a feedback?
Let's ask.
The vortices create heat, and the heat create vortices, and vortices create heat, and then heat create vortices. You know what I mean?
We could ask it some more.
That we would perceive as the Big Bang.
Yeah. In terms of what are visible, the formation of unpaired vortices can be observed experimentally using techniques such as phase contrast imaging or interference microscopy. These techniques allow researchers to image the density and phase of the condensate, which can reveal the presence of vortices and their motion. As the temperature is increased, the vortices become more visible and can move around more rapidly, leading to more dynamic pattern of density and phase variations. In summary, as the temperature is increased from 0 Kelvin upwards slowly in a spinning Beck, the Beck can form a vortex lattice at low temperatures, undergo thermal fluctuations, and form unpaired vortices at intermediate temperatures. Okay, you said, I'm going to copy and paste that, and become more turbulent and eventually evaporate at high temperatures. The behavior of the Beck can be observed experimentally using imaging. Fine. Okay. So I'm going to quote it. You said the Beck undergo thermal fluctuations and form unpaired at intermediate. Can you please be more specific and talk temperatures? Particular event.
Yeah, they're going to go back to that funky equation.
Funky equation.
So ask it, say 4. Maybe.
I won't read all this because this is probably repeating what we've seen. So what would you reckon next?
Like, try for rubidium.
Okay.
What temperature? Like, pick something, because it's
Getting a bit lost, isn't it?
What is the phase transition for rubidium? Temperature.
And how do you spell rubidium? Rubidium.
Something like that. Like that.
Spell check myself.
There you go. Yep. Perfect.
Is it throwing us the same
Going
equation?
to answer the question.
It's interesting because it did say yesterday for helium, it was 2.1.
Okay.
So it's going to give me the same kind of answer. It's going to get annoyed. Oh, 2.17. There you go.
2.17. Okay.
So
Now, is that the first phase transition or the second one?
now that's what I'm interested in. Helium can I So I think this is obviously, this seems like when it goes from being helium to a Beck formation. So if you're going down and down and down and down at 2.17, it becomes a Beck.
Okay. So that's the first phase transition then.
So that's where, as you're coming up.
From zero coming out, that would be where the vortex pairs would be.
Okay, so I'm going to ask, it probably won't know what I'm talking about, but let's ask it anyway. The critical error. Oh, I wonder what it would be for hydrogen. Maybe hydrogen, it could be 2.7, and then we're kind of getting into interesting. So is it saying 2.17? Helium, is it helium 4? Okay. So with helium 4 raise slowly to text
Depends on the external conditions.
Yeah,
so
we're not going to get away from that, are we?
No.
Okay, so it's going to repeat itself. See if there's anything that's not repeated. The critical temperature, onset of vortex. I'm not sure if this is where it could start to be making stuff up because it thinks I've been saying it a lot and it's feeding back into its own conversation.
Yep.
Yeah, it's not gonna, like, if it, as you said, you've already said, like, if it's spinning 10 times as fast in this experiment compared to that, your temperature is going to be completely different for stuff to happen. So it all becomes a bit difficult. And also how much, if your confining potential is 10 times as big in that one to this one, you're probably going to get different temperatures at which things happen.
Exactly. Let's see if I can find anything.
Yeah, you're going to try and use a real search engine.
Yeah.
While you're doing that, I'm going to see if there's any other elements that you told me that are not to do with temperature that
No.
these vortex.
Yeah, it's hard to find. I mean, I think I got that information from someone's thesis. Yeah, I'm not going to worry about that right now. I think the main point is that there's some stuff going on at that very close to absolute zero temperature. There are definitely phase transitions. And it's very possible that the 2.7 degree Kelvin, which is a very low temperature, could be the phase transition of our universe.
There has been some research exploring the potential relationship between the vortex and anti-vortex pairs in Bose.
Oh, nice.
Einstein constant. Creation of positron or electron pairs. However, such studies are in the early stages, and the exact mechanisms by which they may be related to the creation of particle-antiparticle pairs are still under investigation.
Okay, so they're investigating it, which is good. That's really cool that you found that. Yeah.
So what is the connection? One possible connection between Beck and the creation of particle-antiparticle pairs is through the phenomenon of analog gravity. Have you heard of analog gravity?
No.
Analog gravity is the study of systems that can simulate the behavior of particles in curved space-time. We're back to space-time.
Yeah.
Such a strong gravitational field. In particular, certain experiments involving Becks have been proposed as analogs for creation of particle-antiparticle pairs and the strong gravitational field.
And
it's funny that you mentioned that.
Yeah, exactly. And so that gets back to the the medium being a ferrofluid of some sort, because what happens in the ferrofluid is when you put a magnet close to the fluid in the glass, the dipoles, so the little nanoparticles, little nano iron filings line up just like as they would with iron filings, right? And they form these long strings.
Yeah.
So they become visible. So the particles are so small that you can't see them. Even under a microscope, you can barely see them. And you can't see them like in, still have to look at it under the microscope, but under the microscope, when there's no magnet, it's a diffuse system. You don't see any particles.
Just an orange blur.
When you bring the magnet nearby, they line up. They line up. And so they become bigger, really. And then the light can reflect off them because they kind of stretch out. You can actually see them and the light can reflect off them. And that's why you get those patterns. And so it's my opinion that black holes are really just giant magnets, and that they cause these electron-positron pairs to line up so much that they actually appear as electrons and positrons, that you can see them. And so and that's what they see near a black hole. When they look at the black hole at the center of our galaxy, they see a cloud of electron-positron pairs. So it's interesting that it is talking about this, because that's exactly what I'm talking about.
And so I asked something that doesn't seem related to what you were talking about, but it still came back to that. That's very interesting. Is there any research that says these vortex anti-vortex pairs could be related to positron or electron? So is it talking about positron and electron here?
Interesting. So they are researching.
Oh, look, here we go.
They're thinking in these terms.
Look, in these experiments, a Beck is accelerated. They actually do experiments where they accelerate a Beck through space. Really, this sounds fun. You'll get it in the lab. They got a Beck, and
the Beck is experimented through space. That's
accelerated through space, creating a sonic horizon analogous to the event horizon of
a black hole.
Do we believe this? Should we check? I think.
Well, I kind of believe that, because that's what I would expect to see.
Here we go. Accelerating a thin condensate stream to a supersonic speed, and then allowing it to slow again. Physics adventures down the superfluid so it's true. It's not making it up.
That's I'll have to add that to my black hole research.
What happens to the information swallowed by it? Oh, we won't read that. But
and actually there's another article I ran into, which is really simple, just modeling a drain as a black hole.
A drain.
A drain.
Like this.
A drain like that, And then the particles, as they're just about to fall into the drain, have strange behavior, kind of like the event horizon of a black hole. So when they colorize the fluid and look at and follow the particles that are right at the edge, about to fall in or not falling in, they have very complex behaviors, right? And that's why that when I model the Mandelbrot set as a black hole, you have the inner black part and the outer region, but all the real cool stuff, the turbulence is happening at that, call that in an event horizon, because it's got the same behavior as a black hole. In the black hole has something called a photon sphere. I don't know if you ever heard of that.
Mm-hmm.
When they talk about black holes, they talk about the black hole and the event horizon, but they don't talk about the photon sphere. Mm-hmm. And the photon sphere is a spherical region. So you have a outer sphere, mm-hmm. which is the photon sphere. Then you have the inner sphere, which is the black hole sphere. And the event horizon is sort of in between.
Okay.
You know, and that's where so in the photon sphere of a black hole, they claim that the photons, the light, is following strange orbits. They call them orbits, is following complex orbits, mm-hmm. before the light can escape. So in the photon sphere, the light can escape. In the black hole, the light can't escape. But at the event horizon, the closer you get to the event horizon, the harder it is for the light to escape. And that's exactly what I see in the Mandelbrot set. The closer I get to that edge between the black and the inner and the outer world, the more iterations it takes for me to resolve that point. So, so I equate iteration to energy. So the more energy it takes, literally, because it takes more energy for my computer to calculate 1,000,000 iterations than 1,000 iterations. It takes energy for that point to escape the mathematical, the Mandelbrot set. So it escapes a certain boundary, and that boundary I'm calling the photon sphere, right? So there's a boundary where my quasi-particles in my quasi-black hole are being iterated, and then they can escape or not escape. If they don't escape, they actually collapse to singularity, just like they say in the real black hole. In the black hole of the Mandelbrot set, when I iterate those points, they collapse to a single point, in the complex plane. So, the Mandelbrot set behaves very much like a black hole, which is why I call it a quasi-black hole. So I wrote my paper called the Mandelbrot set as a quasi-black hole, because it has a lot of behaviors of the relativistic black hole. Wow. So does a drain, apparently.
Cool.
So, black holes are more ubiquitous, I think, than we think. I actually think the atom is a black hole as well.
Oh yeah, I remember.
The nucleus is the black hole. The electron shells is the photon sphere, and unless you understand the photon sphere of a black hole, it's hard to understand the atom as a black hole. But the electron shells would be analogous to the photon sphere, and the orbits that the electrons make inside the atom would be analogous to the orbits that that light takes in the photon sphere of a black hole. So there's a lot of good analogies, and that in the fractal universe, I want those analogies, because I want the small thing to be the same as the big thing, right? Yeah. So the small thing is the same as the big, or similar, not exactly the same, but self-similar. The small thing is self-similar to the big thing. Yeah. The universe is going to be a lot easier to explain to people.
Yeah.
It's, quantum is different than the macro world. No, I don't want that. I don't want that. If that's true, that's fine. But if it's not true, I'm going to figure it out.
Yeah, that makes it.
Yeah.
So with when I was looking at Distinti recently, his model seemed, I haven't really understood it fully, but it seems to be based on the idea that.
Who's that? Who are you talking about?
Robert Distinti.
Robert Distinti, yeah.
Yeah, he's saying that all matter feeds on ether. It basically, like Pac-Man, just like sucks it in, and then it's like, that's actually very similar to what you're saying with the black hole, or resonates.
Yeah, I like that idea. There's a few others that have that idea as well.
That correlates with what I was thinking about when I started looking into this, just doing thought experiments about gravity. I was like, well, it could be this, it could be that, and I was like, could be just every atom just sucks stuff in, and
Yeah,
then it's like, where does it all
you
go?
just get caught
I
up
don't
in
know.
the flow,
I don't
and you're
know,
just getting
like a
caught in the
drain.
flow.
Yeah,
Yep.
exactly. And then if you model everything like every atom is just a drain, and
Yep.
everything's just going down
Yep.
to it, and
Yep.
it has to be accelerating
Yep.
towards it, not a bit like
Yep.
just if you drop something far away from Earth, it just gets faster and faster until it hits Earth,
Yep.
or with a real black
Yep.
hole. And it's like,
Yep.
okay, well, actually using that model, if you just forget for a moment that it doesn't seem to make sense that everything disappears into a black hole of an atom and you never see it again, that kind of doesn't, it's like,
Mhm.
why would that happen? But if
Yeah.
you just forget that and see what happens, you're like, oh, that explains gravity. And then you can probably go through about 10 other things that's like that would explain that. It would inertia, yep, that explains that.
Mhm.
And then it's like, okay, I can explain all these things with this incredibly hard to believe one thing, but I get to throw away 100 very confusing and
Yeah.
and also quite hard to believe things. So
Exactly. Even harder to believe. At least this is something we can visualize. We
and
see things
simple.
going down the drain, and I know when I put something near the drain that it goes down the drain,
Yeah.
goes in that direction. It doesn't go some other direction, right? So yeah, I think that kind of explanation is kind of interesting. And so in the BEC model, there are kind of like, once the vortex anti-vortex pairs form, you kind of have two mediums, because you have the blank background, which is the BEC, and then you have the vortex anti-vortex pairs occupying the blank. So it's, and you can think of those vortex anti-vortex pairs when they line up. So when you get an unpaired particle and these things are surrounding it, you can imagine that that is what's feeding the particle. So the fluid, the background fluid, it can't move on its own, but these vortex anti-vortex pairs are motion of that ether, that background ether. So they can feed the particle. So these vortex anti-vortex pairs would surround. So an electron, say, would be an imperfection. You can think of it as an imperfection in the BEC, in the perfect BEC.
Is it kind of lost its other half, really?
Yeah. And
So
so
which
then
makes it
and so it's
unbalanced.
trying to neutralize this imperfection in the back. These things are surrounding it to try to neutralize it. And that's kind of the analogy that I think Don Hodson, which I mentioned in my video, I read a bunch of his papers, and that's where I got the idea for the BEC was from him. And that's how he visualized them. So he visualized these vortex anti-vortex pairs surrounding this imperfection, and that the whole purpose of that is that the vortex anti-vortex pairs are trying to neutralize. It's like, this is an imperfection and it's trying to neutralize it. And so it surrounds it, and then you can imagine these vortex anti-vortex pairs are lining up in strings. Like I said, they would line up like magnets, like attached to each other, just like they do in the ferrofluid. They line up in these little needle-like structures surrounding it, and that would be why we have the sensation of electric charge. That would give us the sensation of, it would give us the field pattern of electric charge. So it would actually
Those lines.
It draws out the field lines. Yeah, it is the field lines.
From imperfections.
Like the field is real. It's really a real thing. Vortex
There are
anti-vortex.
lines, yeah.
So then when you put iron filings near a magnet, they're lining up with the vortex anti-vortex pairs in the vacuum.
That are already lined up. And they're already lined up
They're
because
already lined
at
up.
the ends of the lines, there are imperfections that have started to cause those lines to form.
Yeah. So at least it gives a physical meaning for the field line, electric field lines. If the vacuum was nothing, then how do you explain magnetic fields and electric fields? Right?
Yeah.
Like there's
Doesn't
no
make much sense.
explanation. There's no like visualizable explanation that, oh, they just exist. Are they okay? So if if I don't put a magnet near another magnet so that it doesn't, does that field exist?
Mm-hmm.
You know what I
Yeah.
mean? Like, does a field just appear? It's like the virtual particle pairs just appear as soon as you put the, say, a small magnet near a large magnet. No, maybe the field is already there. It's always there, because that's what, that's what the medium, that's what the vacuum is made of.
Mm.
Right.
It's
So,
interesting, like all this stuff we're talking about is kind of I've come to a bit of a realization that you think at the beginning that you're trying to discover what's really going on. And then in the end, you start to realize that doesn't make sense to even be much aiming for that. It's kind of like there is no real. Let's not get into a massive philosophical debate about what is real and what is not, and if it exists and if it doesn't. But in terms of just trying to generate a model, it kind of makes sense to me now. Just say, well, there is no real. Just forget that, and just go, okay, what's the model? And it doesn't matter what it is, but if it explains stuff, if it's simple, if I can understand it, if it makes sense, and if it gradually explains more and more in bits and it kind of pieces together and it's self-consistent, that's all I'm kind of interested in. And in if you're lucky, or if what you're aiming for ideally is something that you end up going, oh, hold on, this is explaining that and that and that and that, and then it all fits together, and it's starting to fit together more and more, and then you end up with something that makes sense, is hopefully more simple than what you've got already, and can give you answers that you already had. But then because it's so simple and it does fit and it does make sense, a lot more people understand it, and maybe you end up getting more answers out of it than you got out of the current hard to understand. And all you're ending up with is you're not ending up with what is really going on. You're ending up with something that we can fit in our brains and exchange with each other. And that if you once I've realized that's what I kind of am aiming for now, things become a lot. I'm not getting panicky about whether am I really describing what's really going on? No, it doesn't matter. That's all irrelevant.
No, it doesn't. And so, exactly, and that's why in my video I asked the question, can there be an ether? Instead of is there an ether or isn't there an ether?
That's not a real
Can
question.
there be one? And if there is, what model would best it? And can it explain things better and easier than what we currently have? And if it can, then like you say, other people can, it's more accessible. So other people, inventors, might be able to invent something once they, with this model, if it's close to the truth, right? If it works and it's close to the truth, then maybe someone will be able to figure out free energy with it.
Possibly.
Right? That's my goal. Like, obviously, that's what everyone's doing. Everyone's studying Nikola Tesla and doing all this stuff because they want to figure out free energy. We want to see if it's possible. Is there something, that we can do that is that will give us free energy?
I mean, beyond free energy, there's a couple of other ones that you could get out of understanding a lot of this stuff, and one of them is computational ability, like quantum computing. Given that some of these things maybe just don't make sense, like entanglement and other things, they may be going down possibly a dead end.
Right.
But realizing that could be quite powerful because you don't waste any more time. But also, you may think, oh, well, okay, so that doesn't work. But you can compute using, tiny bits of ether or something, or, doesn't matter what. But once you understand it, you can maybe compute it. And that's not free energy. That's not free power. But it is, if you can plug into an incredibly intense ability to compute, that isn't necessarily quantum computing, that's like a whole new world opening up instantly, or not instantly, but so computing power, real power. I mean, there's a bunch of others, like obviously chemistry, obviously travel, physics, all this stuff. That's not power and energy, but it could transform huge things, climate. there's tons of stuff. That's how I originally got in this, interested in this, is how could we get ourselves out of problems to do with food, climate, and energy is obviously massively key to that, and environmental stuff. If you've got lots and lots of free energy, or not very cheap energy, you can suddenly afford to not destroy the world quite as quickly as you.
I mean, it could go either way. I mean, if everyone
just
had
destroy it instantly,
we would just destroy it faster, probably. Yes. But and that's maybe why, you know, if free power is being hidden from us or whatever, I don't know if it is. You know, that might be one good reason. Like if everyone had free energy, we don't know what kind of world it would turn into.
We could just boil ourselves.
That's kind of a little scary, like a scary thought. You know, like sci-fi kind of scary.
Yeah, exactly.
But you know, it's worth a try. It's worth a try.
Okay. So. Well, I think I am quite impressed with, like, when you dig into the detail, you can get lost in the weeds pretty quick, like with these temperatures. But I think the trick is to sort of come straight back out, and like a couple of these things, you know, especially that last one. It's like
it brought up something that was really interesting. And I remembered that, I think you shared something with me that brought that up, and I thought that was really, really cool, with the black hole vortex anti-vortex pairs near a black hole, which they do see, which are real, but they don't call them real, they call them virtual. It's so like I these talks, they talk about, they're still calling them virtual even though they can see them.
Yeah, we've got a picture of them, but they're still virtual.
But they're virtual. They don't really exist. Where did they come from? Well, I think I know where they came from. I think that they're there and you just raise them up. It's kind of, I like to call it raising them up. So in the vacuum of, they're not. So in the vacuum, they're not electron-positron pairs. They are something. They are something else, right? They're not electrons and positron. Just like when you take sodium and chloride, right? When you put them together and make salt, it's no longer sodium and chloride.
No, it's not just
sodium has different properties. Chloride has different properties, and when you put them together to make salt, it's salt. It's not sodium and chloride.
Yeah, if you
sodium and chloride lose their identity and they become salt. So it's the same thing. The electron and positron, when they fall into the vacuum, they lose their identity as electron-positron pairs until we bring them out, until we raise them up to which is what seems to be happening near the black holes. So, and in any experiment where they need a virtual pair to appear while they're there. They're not electrons and positrons. You pull them out for a second because you need them, and then you put them back. I don't know how they do that, but you know, that's another important point, is when the electron and positrons annihilate, technically they are annihilating because they're no longer electrons and positrons, but they don't disappear. I think that's the important point. They don't disappear. They just become the medium.
Become the medium.
They go back to where they came from originally. Yeah.
That does make more sense to me.
Yeah.
When you said about this, like, obviously, if you develop this model, or lots of people develop this one, and this ends up being a model that really explains things well and gets used in the way that we're talking about, do you think, like, these vortex anti-vortex pairs, they're kind of seem fundamental in terms of the model as you're looking at it, but obviously thousands or millions of years into the future, if people are sort of digging deeper and deeper and understanding better and better, it's easy to imagine how you then get into, oh, well, we've worked out what we think the model is for the vortex or anti-vortex pairs, and then another X thousands or millions of years, they work out what the thing that do you imagine that this is, or kind of, do you see it as having to be fractal? I mean, do you see that does it not make sense? It doesn't make sense to me
Yeah.
that there's a point where at some point civilization or whoever's investigating this hits something and goes, oh, that's the bottom. And then, you know, a million years later, they're still investigating. No, they were right. It was the bottom. It is the bottom.
Yeah.
But, you know, that is the fundamental thing. And there's not anything, and it makes complete sense for that to be the fundamental building block of everything. And it's like, I don't know if that is logically possible for you to actually ever hit the bottom.
Right. Well, the bottom would be the absolute zero.
Oh, not temperature. I mean, physical things.
Yeah. So
what we call matter.
And so where the fractal comes in my opinion, is in the phase transition.
Okay.
So before phase transition, it doesn't have to be fractal. Phase transitions are what, in chaos theory, phase transitions seem to be where fractals appears. Now, fractals are emergent properties, so fractal is not the input of anything.
Okay.
Right? It's not like, oh, here's a fractal to create something. No, fractal is an emergent property of something else, and usually, very often, it's in a phase transition. So I've found this like many, or at the edge of something, you know, the phase transition or the edge of something. So at the edge of the black hole, or at the edge of the drain I was telling you about. Actually, I forgot to tell you that they found sort of fractal patterns in there. Okay, these complex orbits that they were seeing had the property of self-similarity. The other place I saw it, which is really interesting, is in the phase transition from a metal to an insulator. So there's an article I found that talked about a paper on turbulence, but it's called Fractal Electrons on the Brink. The article is called Electrons on the Brink. And they talk about, so what they do is they, making semiconductors, right? So they take a material that's a conductor and they dope it with something, and then they turn it into an insulator, or in between, like a semiconductor. But so what they found was they take a metal. So in the metal, the electrons kind of spread out over the metal. So when they do an imaging, they do this kind of imaging, I can't remember, they image it and they can see that the electrons are spread out over the metal, over the material. And then, electrons on the brink.
Yeah, I'm typing it in.
Yeah.
Fractal patterns. I think may have seen it.
Okay, I might have sent it.
I have seen it actually. Yeah.
I mentioned it, from time to time in my videos. So, and so at this phase transition between metal and insulator, they see fractal patterns. They see the property of self-similarity. So when it's a metal, the electrons are spread out over the material. When the material is an insulator, the electrons are kind of clumped together. So that they can't conduct anymore. It can't conduct anymore. In between, when it's phase transitioning from a metal to an insulator, they see the property of self-similarity. So they see a different pattern that looks like it's that has a scaling law. Okay. So that is like, so that was my first clue that, oh yeah, it's phase transition, that's where you see fractals. So fractal is not the input of anything. I think that's an important point. It's not. And, if we go back to the beginning, if we go down through the phase transitions, the original Bose-Einstein, the vortex-anti-vortex pairs don't necessarily have to be a fractal pattern. I'm not saying they're not a fractal pattern. I think they could scale in a fractal sense. So I think they would, in 3D, they would form tetrahedrons, and that these tetrahedrons could have tetrahedron, it could also be a fractal pattern.
Do you mean if you could dig into what was inside one of those vortexes, you may see other vortexes making it up, or other
there could be turbulence. So turbulence is another place where they find fractal patterns. So anytime there's turbulence or phase transition, a phase transition that creates turbulence, that's it, that you'll often see the property of self-similarity in those patterns.
Okay.
So
So, and
that's,
that is what a vortex is. It's a turbulence, isn't it? That's all
yeah,
it. It's
yep,
just
yep,
something
yep,
spinning
yep.
in a medium, which is
Yeah, well,
turbulence.
it depends. There's different kinds of circular flow. If you have, if the flow is not spinning, I think it's called irrotational flow, and it may or may not have turbulence. So it's really where you see turbulence that you would see these kinds of fractal patterns forming.
Actually, it's a very weird thing that just very briefly before I started to get into this whole physics thing about 6 months ago, I went on a thing where we were at a lock or somewhere next to a river, and the river was combining, and I could see all these
Mm-hmm.
eddies, and they're kind
Yeah,
of moving around in straight
yeah.
and forming together and stuff. And I was
Mm-hmm.
looking at them thinking, they're fascinating.
Mm-hmm.
And something that drew me to them, I didn't have a clue why, but I found them like, oh. And then now we're discussing it, it's like, well, actually, there it could be like, what is at the root of everything is like little kind of spinny vortexy things that, different sizes of them and different combinations, and the way they pair up and move creates spindles of them, and you end up with what we've got. So it's
Mm-hmm.
kind of interesting that I was drawn, for me, to that turbulence and a
Yeah.
little vortex.
Yeah. If you could look something up, I gotta go pretty soon, but if you
Yeah,
could look
I'm gonna have
something
it.
else up, do a search for something, turbulent black holes. There's
Okay.
another article that's really interesting that you might want to have a look at. It's related to what we were just talking about.
Okay, great.
I think the article was called Turbulent Black Holes.
Let's type it in, turbulent. There you go. That's the one. So
that is
rapidly spinning black holes can be display turbulent gravitational waves.
that is the paper. Yeah, that's the paper that talks about it. And Lewis Lerner, actually, he's one of the researchers at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, in right down the road from where I live. So a lot of famous researchers, a lot of high-end researchers, physics researchers are working with the Perimeter Institute or teach there. So he's one of the researchers from there.
Give me a sec.
So yeah, so that's an interesting one. There's also an article. The article is more interesting. So I don't know, I can't remember what the article is called, but I go back and see if there's an article associated with that. Sometimes articles are easier to read than papers.
Oh yeah, there was a shorter version. Okay, so
just
I think it works out pretty well in terms of I've learned a lot about
Yep.
your model, and I'm really interested in that. And then in terms of ChatGPT, I think we know a bit better what kind of things to ask it, and we've learned a bit from it, and
yeah.
I enjoyed it.
Yep. Yeah, we can keep working with it and see if we can extract any more. I think this will be an interesting tool for other people to use as well. But we are going to, be wrestling with the mainstream interpretations and,
Yeah.
But I think it is interesting that you got it to say that there is a possible connection between BECs and particle-antiparticle pairs, which is, it's good to know that at least someone's doing research in this area, because maybe it will be able to be validated or vindicated somehow.
Yeah, I think this is where it becomes very powerful in terms of it kind of directs your understanding a little bit, in that we were talking about vortex anti-vortex pairs being, your theory is like positron electron, maybe they're related to positron electron. It's like no one really in the mainstream or even on the web would find that statement.
Exactly.
But you throw it at it, and it comes back with, oh, they're actually, doing stuff which kind of is highly related to that concept. And Google wouldn't tell you that. If you type this in Google, you wouldn't get this description back, and then you wouldn't be able to go and find this article.
Yeah.
So it's kind of it's a kind of key into a world that we haven't really had access to. Which I find, and it also gets you thinking about things in a different way, or it's gets
I think I'm
me
going to start using this more as a search engine. Right.
And just a conversation guider is kind of useful. It's like, oh, we're talking about this. Let's see what this third party thinks. And it's like, oh, well, it thinks this, or it knows about that. I mean, really, it is incredible. You've basically got an eye into all of humanity's wisdom and knowledge.
All of our research that's ever been done.
That we thought we already had with Google, but we didn't. We had some search results on Google. Now we've got we've got search results, but intelligently provided by something that understands them. Oh my God. It is. And this is just the crappy version, isn't it? This is the first not very good version, because it makes stuff up and it lies to you, but it's still amazing. I'm impressed. Cool. Right, I'm better head off.
Okay. Well, anyways, I should probably go make dinner.
Yeah.
This was a good start, I think.
Yeah, I enjoyed it.
So you will be able to send me the video?
Yep, I'll upload it to Drive.
Okay.
And then it will become amazing.
I think I might just edit out the beginning. I might I don't know, I might not edit too much and just put it up. And I think my YouTube subscribers will enjoy this conversation as well. So I think it would be good to give them access, if that's okay with you.
Yeah, definitely.
The only thing is, obviously your name is going to appear, and hopefully that's okay with you.
Yeah, that's fine. Yeah.
Okay.
Okay. Right then. Excellent. And then we'll do maybe a second version in a few weeks or something.
Yeah. In a couple of weeks.
Dig a bit deeper.
Sure. Okay.
Perfect.
Sounds good.
Thanks.
Okay.
Nice to see you again, Laurie.
Yeah.
Bye.
Yeah. Have a good night.
And you. Cheers. Bye.